Good day. My name is David Ronin Reyes, and I'm part of Group 4 under CPE 107L Section B2. For our Lab 7 vlog, we were actually given three tasks. So first, we have the counter design using JK flip-flop of the 180 count. We also have the second task, which is the decade counter using a D flip-flop that counts up to 180 or 3 minutes. And finally, we have the Modulo 6 counter using SR flip-flop. We have three tasks, each divided to one of the group members. And so for my part, I'll be doing the last task, which is the Modulo 6 counter using SR flip-flop. What I'll be doing is a counter that counts 0, 2, 3, 6, 5, and 1 and repeat the sequence. So in order to do that, we'll be using the Logism application and the Microsoft Excel. So here I have on my left, I have the Logism application, and on my right, I have the Excel file, which shows the truth table I have already created. So, I'll just zoom it in. So, as you can see, we have the present state, which is the Qt2, Qt1, Qt0. So, this is because our counter is actually 3-bit. So we'll be displaying or we'll be counting the numbers as I mentioned a while ago 0, 2, 3, 6, 5, 1 and repeat that sequence. So that means the next state of 0 should be 2. So with this we have the decimal value here 0, 2, 3, 6, 5, 1 and we have the binary values on this part for the present state, which is a 3-bit. So for 0 we have 0, 0, 0, for 2 we have 0, 1, 0, for 3 we have 0, 1, 1, 6 we have 1, 1, 0, and 5 we have 1, 0, 1, and lastly we have 1 with the value 0, 0, 1. Now, as I mentioned earlier, the next state will be the next value. So for 0, 0, 0, or for 0, we have the next state value of 0, 1, 0, which is 2. So that means the value for 2 in the next state is 3, which is 0, 1, 1. The value for 3 in the next state is 6. The value of 6 in the next state is 5 and the value of 5 in the next state is 1. And finally, we have the last value of 1, which brings us back to the first digit, which is 0 here. So we actually have to use three flip-flops for this given. So I've actually made this part of the truth table, which is the SR2, SR1, and SR0. So why SR? Because we were instructed to use the SR flip-flop. So as you could see, we made three uh, colored SR flip-flop tables. So one for each bit for the present state and for the next state. So how did we get these values under these tables? So we made use of the excitation table for our SR flip-flop, which states that Qt, we have these values, and Qt plus 1, we have these values, which results to the value of these for SR. So we have uh, 0, 0, and we get the value of 0, x, then 0, 1, we have the value 1, 0. 1, 0 is equal to 0, 1, and 1, 1, we have the value x, 0. Now, I've actually made it easier for us to understand by using a color-coded system. So as you could see, this Qt area of the table symbolizes the present state, and the Qt plus 1 symbolizes the next state. So as you could see, we have the value for our first column. So we get 0 and 0. So as seen in our excitation table, for both values, if they are both 0, we have to put 0 for S and X for R, which we have done for this SR2 table area. So when we move on to the next values, which is still the same, 0, 0, we get 0x. Now 0, 1, we get the value uh, 0, 1, we get the value 1 for S and 0 for R, which is here. Then when we put 1 and 1, we get the value x and 0. So that goes on for all columns. So qt2 and qt plus 1, 2 is for SR2, while SR1 is for the middle columns, which is qt1 and qt plus 1, 1. And finally, our qt0 and qt plus 1, 0 is the SR0, or our last column, which is the green parts. So with these data, which we were able to get with the help of our excitation table, we could now create our K-maps. So here is the K-map I have created earlier. So this, as I mentioned earlier, I made it easier for us by color coding the systems or the K-maps. So this, as I've said earlier, is orange, similar to this one, which is SR2. So these values are for SR2, these are for S1, I mean, and this last green K-maps are for S0. Now, we've actually explained how to create or how to understand K-maps from past lessons. So I'll just explain what I made here for to make the length of the video shorter. So I actually have a legend here, which means Q2 is equal to A, Q1 is equal to B, Q0 is equal to C, Q2 prime is equal to A prime, Q1 prime is equal to B prime, and Q0 prime is equal to C prime. So based on the data there that we have collected a while ago, we get the value S2 is equal to BC, and using the legend, we get the value S2 is equal to Q1, Q0. So we actually get these values for all the numbers or for all parts of the SR flip-flop. These values will symbolize the inputs for our SR flip-flops. So upon observation, we could say that we will make use of 4 AND gates, or 1, 7, 4, 0, 8, and IC. So here 1, 2, 3, and 4. So we'll be creating our circuit using the Logism application. So let me just transfer it here to our left side. We'll be using a clock, and then I'll need a SR flip-flop. We'll need 3 of these, and then AND gates. So gates, let's pull out the AND gates. So let me just lower this ones down, and then to make this shorter, we have to put 2 inputs, gate size to narrow, so that will be saving space. So here we go. And then let's just copy this. Control C, Control V. Con and then here for the last one, we'll be needing 2 for that, for this last one. So let's first connect our clocks for each flip-flop here, and then finally here. Wait, there we go. So according to the table for our S2, wait, I'm gonna label this first. SR2, SR1, SR0. Now let's me just move the labels, which I apparently cannot do. Wait, I'll just delete that. Move delete these, and then just retype SR2 there. And then we'll be needing another SR flip-flop for that one. So this will be our SR2, SR1, and finally as our SR0. So first we need an input for our S2, which is Q1. and Q0. So Q1 is this one, Q1. So we'll be needing that here, Q1, and then Q0, which is this one. You just put it there, Q0. And that is for our S. So we're done with our S. Now R2 is Q1 prime, which is this one, Q1 prime. Let me just drag it there, Q1 prime. There we go. Now S1 we have Q2 prime and Q0 prime, Q2 prime, Q2 prime, and Q0 prime, which is this one. And that's for our S1. For our R1 we have Q2, which is this one. And finally, for our last flip-flop, we will make use of Q1 and Q0 prime. Q1, which is this one, Q1. And then, oh, so we've actually, there, I've actually connected it. And then Q0 prime, which is this one, the green one. So let's just connect that there. And then Q2 prime and Q0. Q2 prime. And then Q0, which is this one, which is our R. So this is our S. Now, to make it easier for us to understand, I'll just put outputs, output pins to represent our Q for each of these values. North. So Control C, Control V. We just move that forward there. So our Q there, and then this one, and then finally this one. There we go. Now let us check if it works. So let's go back to the truth table. So for our, we should have the output 0, 0, 0, followed by the 0, 1, 0, then 0, 1, 1, then 1, 1, 0, then 1, 0, 1, and then 0, 0, 1. Now let's simulate. First, we have 0, 0, 0, then it should be 0, 1, 0, and then it should be 0, 1, 1, and then it should be 1, 1, 0, and then 1, 0, 1, and then lastly 0, 0, 1. Now to ensure that it actually repeats, let's try it for a second round. So after this, we should have the value 0, 0, 0 again. Okay, then 0, 1, 0, then 0, 1, 1, and then 1, 1, 0, and then 1, 0, 1, then lastly 0, 0, 1. Okay, so we've actually made use of 4 AND gates and 3 SR flip-flops. So just to test if we could create it using the 7408 AND gate, let's try creating one right now. So we'll just make use of the clock again, just to show if it is possible. SR flip-flop, and then another one, and then another SR flip-flop. So let's connect our clocks. And then let me just return to our K-map. Now we'll be using one AND gate first to connect all of these ones. So first Q1, Q0, which is this one, Q1, and then Q0, Q0, which is this one. And then this should be inputted here. Then we should have Q1 prime, which is this one. So we no longer need an AND gate for that. Q1 prime, Q2 prime, and Q0 prime for our this one. So Q2 prime, and then what? Q0 prime is this one. There we go. And this should be there S, and then Q2 for our R, which is this one. There. Now for our last one, for our last flip-flop, we have Q1, Q0 prime, Q1, just this one, Q1, Q0 prime. This would be our S, and finally Q2 prime, which is this one, Q2 prime, and then Q0, which is this one. So let's once again put some output pins. Let me just Control C, Control V. This ones have them face south. There we go. Now let me just connect them. There, and then there. So let's simulate, and we should have these results. So first 0, 0, 0, then 0, 1, 0, then 0, 1, 1, then 1, 1, 0, and then 1, 0, 1, and then 0, 0, 1. And then let's repeat it to ensure that it actually repeats the sequence. Should be 0, 0, 0, 0, 1, 0, 0, 1, 1, and then 1, 1, 0, 1, 0, 1, and then finally 0, 0, 1. So that's it for our Modulo 6 SR flip-flop. We've created one version with the use of 4 AND gates and 3 SR flip-flops, and then another version with 1 AND IC, or the 7408 AND IC, and 3 SR flip-flops as well. So this is once again David Ron Reyes of Group 4 for LAB7 Vlog Modulo 6 counter using SR flip-flop. So thank you for watching.